Hello, I would like to do a quick sound check before we start. If you can hear me, please type yes in the questions tab. Okay, great. We're seeing some answers come in. Thank you. Hello and welcome, everyone. Thank you for joining us today for our webinar titled Productionalizing H2O Driverless AI Models. My name is Patrick Moran, and I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker. Nicholas Pung is a partnership software engineer at H2O.ai. Prior to working at H2O, he worked as a quality assurance software engineer developing software automation testing. Nicholas holds a degree in mechanical engineering and has experience working with customers across multiple industries, identifying common problems and designing robust automated solutions. Now, before I hand it over to Nicholas, I'd like to go over the following housekeeping items. Please feel free to send your questions throughout the session via the questions tab. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slide deck will be made available after the presentation is over. Now, without further ado, hand it over to Nicholas.
Hi, everyone, and welcome. Good morning to anyone on California time. So today we'll be talking a little bit about productionalization of models and having kind of a focus on driverless AI specifically, which is H2O's enterprise product. So before we get started, just a quick introduction about H2O specifically. So what are we? Who are we, right? So we are based out in the Silicon Valley in Mountain View, California. We were founded in 2012 and funded by, as you can see on the page, several I don't know, fairly large companies, if you want to call it that. And initially we started out in the open source. In fact, nearly 20,000 organizations are using our open source platform today for their machine learning purposes. And more recently, we created H2O Driverless AI, which is our enterprise platform, and we'll talk about that a little bit further. In fact, today this number is a little bit off, but we're closer to about 200 folks in our global scope, and we are located primarily in Mountain View, California, but also New York, London, Prague, and India, and small satellites throughout the world. Just a quick highlight of our product suite. So we do have, again, the open source, which is on the left. You'll see H2O, which is the kind of core open source suite, followed by Sparkling Water, which is essentially our H2O3, but also integrated directly with Spark. On the right, which is what we're going to focus a little bit more on today, is H2O Driverless AI, which is our enterprise product. It's designed specifically for data scientists as a tool, allowing for complex automatic feature engineering, as well as machine learning and interpretability. So just before I get started, I always like to point this out because it is useful for folks in general, is that we have a community Slack. I welcome everyone to join, mostly because this gives good opportunity for you to ask questions, gain more insight, just generally get more information on a day-to-day basis rather than having to search through, webinars and videos and, old stack in GitHub or something like that. So feel free to join. The link is here in the slide deck, which we'll also share at the end of the presentation. So we'll talk a little bit about putting models into production here. So this is kind of high level, what would be kind of the, I don't know, productionalization pipeline, right? So it starts with the data engineering. Your data is probably sitting somewhere in a Hadoop cluster or in maybe a SQL database, or maybe even both. Like some people have some data which is stored in SQL, some data that is stored in maybe MongoDB in a NoSQL format, and then some in HDFS as well. And what it really takes is some engineering to get the final table that the data scientist actually wants to use of all the data that they want to use. At which point then you will do some feature engineering, actually train the final algorithm, and then create a final model which you can get some training predictions to run validation on, or verify that the model is good. At any given time wherein you find that the model itself is good, then you will push it to the actual deployment or to production, right? So this is essentially the idea of, now I'm serving for customers, now I'm serving for maybe internally only, but basically getting predictions that will have effect in real life. Here in the above box here, it's kind of just testing. It's like staging. You're not doing anything that will directly influence the company as a whole. But in production, you will. And again, you will have to understand that there is the feature engineering must happen. Then the data engineering will have to happen to get the, again, kind of standard format table. And then there will be the actual pipeline to do the feature engineering that was originally done. The model will then score using these engineered features. And then these predictions, which are the production predictions, will then be used by whatever production stuff you have. So maybe it's an application that sends the answer to the customer. Maybe it's just a score back to the database so that you can actually use those predictions internally. But that's kind of the idea. Now, what I've done here is I've kind of highlighted a couple things, but this is kind of the division of work, right? Oftentimes you have several different people that are doing several different things, and ultimately your pipeline, which looks fairly seamless initially, is now broken up into multiple different people. This could be teams of people, this could be just a single person in a smaller company, but you often will have a single data engineer or a group of data engineers who do the actual original engineering from taking the original data and creating the data that a person may need, for the data scientist may need. The data scientist does all the kind of like model pipeline training the actual model itself. And finally, there's this machine learning engineer who then takes the model that the data scientist has then given them, as well as the feature engineering pipeline, and then has to push it to production. And in certain instances, that can be very complex, depending on how complex this feature engineering process is, just what kind of algorithm or model this is using. And so what we end up having is certain challenges, either based on the limitations or expectations of the business, or the limitations and expectations of the environment in which production is existent. Sometimes from the business, people will ask, well, this is an application, so it's scoring to a customer directly. Customer presses a button and they want their answers back ASAP. So I need to have millisecond scoring time, and I cannot have anything else. And so what this eliminates oftentimes for the data scientist originally is more complex algorithms. But at the same time, the business is saying, well, not only do I want millisecond scoring, but I want it to be super accurate. And this adds an interesting complexity, because simple models score really fast, but simple models are also very bad, or not very bad, but are not as good as more complex models. You also sometimes have to adhere to legal or governance expectations, meaning that, for example, in healthcare, you may not want to bias yourself against one kind of ethnicity, or in banking, you may not want to bias yourself against the gender when making predictions. So, for example, if you're increasing loan rates for only males, this could be dangerous. And so from a legal or governance perspective, the model needs to make sure not to include this bias. There are other things like how the production environment works, where you need to swap out the model almost seamlessly, meaning that one model must go down immediately as the next one comes up, and the models cannot have any downtime or shift in between. And this is things that are often handled by the environment itself, but do come as a complexity. There are other things like, Python is a very common language for data scientists, but not always in production. Sometimes you're required to run your models in Java, in which case then the machine learning engineer's core task is actually taking everything that the data scientist did in Python and replicating it in Java. So you're basically rewriting your entire pipeline twice, which is kind of crazy. So just in the interest of time, we're going to kind of move forward, but there are a lot of different concepts to kind of consider, things like difference in hardware, software on development and production environments as well is another one. How much access to the internet a model might have. Apologies, this is a spurious slide. So how does driverless AI approach this process of creating a model pipeline that's easier, more flexible, and less complex to deploy? How do we get it into production? So we have two different methods. We have the Python scoring pipeline, and we have the Mojo scoring pipeline. In fact, I will be focusing primarily on the Mojo scoring pipeline. And in most cases, this is what we at H2O recommend in terms of using as a production level score. But just as a high level, the Python scoring pipeline is essentially a pipeline, or rather all driverless AI pipelines contain three things. And I'm making the assumption that some of you all have some level of understanding of what driverless AI does as a whole. But driverless AI does multiple things, which includes creating those feature engineering features as well as creating the final model. So the pipeline itself, the expectation coming out of driverless AI is that the pipeline itself does all the feature engineering as well as the model tuning. So the pipeline itself must do the feature engineering and the scoring. Python scoring pipeline has both of these aspects. Basically, it ships as a wheel file for easy installation. You do like pip install file.wheel, and it can be installed into any Python pre-existing environment quickly and seamlessly. You can see the documentation here. The Mojo scoring pipeline is originally used to stand for memory optimized Java object, but in the recent releases of H2O Driverless AI, we now have it as ability to be scored in multiple different language environments, Java, Python, and R. It's lightweight and highly portable, and it's designed to be minimalistic in every aspect possible. So it's designed for extremely low latency scoring. It's also designed for having as little dependencies as possible, and we will try and cover this, time permitting, in a live coding session. But basically, if you take a look, you can also see in the documentation in the link below. So what does model productionalization mean in terms of what driverless AI does? Well, if we talk about the original kind of pipeline, so we'll rally back again to that one graphic, but the data engineering still has to happen. Now, one thing that I did forget to put is another box right at the top here. So where it originally said data scientist, this is what driverless AI would do. So in fact, we could actually have a box that kind of covers this entire, this entire section from this area, from like model pipeline building and the model deployment inside a box that says just driverless AI. Because driverless AI will do the training aspect of your model, but it will also help create an artifact, the Mojo and Python scoring pipelines that allow you to push to production quickly and easily. So, so how do you get access to this? Basically, the access to the scoring pipeline itself comes as a result of the completed experiments. So once you've completed an experiment in driverless AI, you can either click the download button, which is there for everyone to see, or you can gain access to it via the Python or R client for driverless AI. There's a method for downloading specific artifacts. Dependencies are also available from the completed experiments page. They come packaged along with these files. You can also download it from the driverless AI resources tab, which is here, so you can see the Mojo 2 Java runtime as well as the Python runtime. or in Java specifically, we have it, via Maven or as a Gradle project. So just kind of as an example here. Cool. Additionally, as I was talking about the fact that driverless AI does encompass a fair majority of kind of this pipeline, we also have internally in the driverless AI application the ability to make deployments directly to things like AWS Lambda or to a local REST scorer that allows you to kind of test behavior of a model quickly in production in ways that we've done in the past. You can kind of see the documentation here, and then there are also these two links which we'll cover kind of moving forwards. Cool. So what do real-life solutions look like? Well, for us, there's a couple different ways that we've gone about it. You can see them in our templates and examples repositories. These are open source, so they're very easy to see. We have several different examples. The first one is a REST server. So essentially, this is what I was talking about initially, wherein, oftentimes customers will make a request via an application. It will send that request downstream to your scoring server somewhere via the internet, probably, at which point the scorer will make a score based on the information provided by the customer's application, and then come back with an answer. And the answer will be, again, responded back to the customer specifically. And that's kind of the idea of having like RESTful server deployment. Can be done via HTTP requests. And inside our DI deployment templates, we have automatic generated API, which basically provides you the ability to gain access to multiple different endpoints. In development, things like, the model schema. So like actually understanding what the model inputs are required. But for the customer specifically, scoring multiple inputs or scoring a single row can be done via different API endpoints. The reason why I will point out AWS Lambda, and I don't want to focus so much on AWS so much as cloud. The idea of having the Mojo deploy in a cloud environment. So like the reason why I point out AWS Lambda and SageMaker is because they are different methodologies for deploying into a cloud environment. Lambda being basically like serverless deployment, SageMaker being a concept of containerized deployment. So meaning like deploying maybe the REST server as a Docker container, which can scale potentially. Alternatively, we also have in the works, and there is an example of this, of scoring against a SQL database. And I know I talked about it earlier, and so we do have in review currently another template. So basically, the difference between templates and examples is that templates is what we would say are maybe slightly more production ready. They're more maintained. We take a significant amount of time to make sure that the code is good, as opposed to the examples wherein the code may be a little bit less clean, maybe slightly more dirty. And also, they work in a single instance or in a single occurrence of us, having tried it in a POC. Cool. So we're going to move forward just a little bit here, assuming my button works. There we go. So things to consider, right? How do I scale my deployments? So things like Spark come to mind, right? Things like Kubernetes. Or other container services, maybe Docker Swarm, or none else come to the top of my head, but basically the ability to maybe mask the container or service behind a load balancer and have some orchestration layer that basically spawns containers on the go, or partitions data in Spark successfully in order to not overconsume or in order to avoid out of memory or slowness. So things like that are quite interesting, and the way that the Mojo handles it is by being as portable as possible. It can actually be scored in Spark using some of our sparkling water APIs, meaning that you don't even have to have sparkling water. You need to have a single sparkling water dependency, which is quite light, and it will actually score in your Spark infrastructure. So provided some understanding of what the Spark infrastructure looks like, you can actually score across your entire Spark cluster. You can score across part of your Spark cluster as you would normally define it in your own kind of infrastructure. Kubernetes is also really cool. We've done examples in the past, which I don't have here. Is my screen not being shared? I apologize. I don't realize why my screen kind of didn't share, but I'll share again this one. Okay, cool. Apologies for that. We'll start sharing again here. Seems that something went amiss. Okay, so this is the original screen. Everything that I said kind of holds sway still, so I want to push forwards a little bit just so that we have enough time to kind of discuss other things. But moving forward to through Kubernetes, through scaling, through application, through things like Spark, we come upon dependencies. Be sure to consider your dependencies. You know, how big is the data? How wide is it, right? Even if I'm scoring a single row, if the data is 1 million columns wide, it's going to require different requirements in terms of compute resources than something that's, you know, 50 columns wide. Or maybe I'm actually scoring batches of 1 million rows per attempt, right? In which case my infrastructure will look a little bit different. You maybe want a more higher memory machine, but lower CPUs for something that is millions of rows, but very skinny, meaning like only a couple columns. You know, other software dependencies need to be resolved. Things that make things complex in production is having scikit-learn pickles, having you know, pandas, having NumPy, having all the other additional feature engineering modules in Python, and I apologize, this is all going to be based off my Python knowledge, that one might use for feature munging, even before scoring the pipeline. These things is one of the things that the Mojo tries to resolve by minimalizing these dependencies as well. You know, you also have to consider access to the data. The closer the score is to the actual data, the more effective it will be. You know, if you're scoring right on top of your Hadoop cluster in an edge node, it's a lot easier than if I were to score on a platform that is going via 2 proxies to my Hadoop cluster. Again, talking about resources, making sure that we have enough resources, that the resources are applicable to what we're actually doing. In the case of, you know, Java, if I don't apply enough heap memory to the JVM, I might end up running into out-of-memory errors or things like that. So, you know, things to consider as far as, you know, requirements and dependencies. Cool. So we're going to do a quick demo. Just wanted to make sure there's no other slides after this. But with this demo, I'm going to start. I'm going to start with driverless AI. So this is driverless AI. I will avoid going through, excuse me, let me log back in. But this is the original driverless, or this is driverless AI. Basically what it's going to give to you available is, after it finishes running some tests, is going to give you a data sets page. We're going to avoid most of these things in the sense of we're not going to talk about them. The 2 things we're going to talk about are the experiment itself and what the experiment kind of encompasses in terms of creating of a final pipeline. So just while this finishes testing, we're going to talk about this. So we're going to say, okay, the experiment encompasses the model pipeline, and then we're going to talk about the actual deployment. So we're not going to talk about any of the other kind of peripherals of driverless AI. So that's what we'll do. Okay. As this may take some time, and just to kind of avoid waiting in dead air, I'm going to show you guys right now driverless AI deployment templates, which is the repository. Couple steps as far as, you know, building It's pretty straightforward. Basically, all you need to do is run /create_new and then distribution zip, and it will actually build all the templates for you from which you can pick and choose the ones that you want. And basically, we have a couple different options. The reason why I think this is super important to understand is just kind of the level of flexibility that the Mojo provides. It allows you to do something like a local rest score, or actually this can be deployed anywhere. It can be Dockerized, it can be run as just a JVM, it can be any kind of level of thing. And so this being as atomic as it comes, then allows you to have more value in inserting it into the greater picture without added levels of complexity. Hope that kind of makes sense. Well, this is going to take the time it's going to take, unfortunately. I didn't expect them to be started. Okay, so moving forward. So in fact, just because of the fact that we're still kind of waiting, I'm going to kind of skip forward just a little bit, and we'll rally back. But what happens? I want to give an example of like the lightweightness. Excuse the awkwardness of that phrase, but of the Mojo itself. So what I have here is an environment, a Scratch environment for the Python Mojo scorer. Okay. Now, if we look inside of it, there's a couple different things. This DAI Mojo wheel file was downloaded directly from Driverless AI. And the mojo.zip is what is called the basically final scoring pipeline. And if you unzip the mojo.zip, you'll get this Mojo pipeline. So if I ls look into what the Mojo pipeline looks like, you'll see a couple different things. You'll see the Java runtime dependencies if you choose to use Java. You'll see this guy, which is kind of important, but the pipeline.mojo. This is the actual scoring artifact. It's basically the only thing that matters in all of this. The rest is all kind of peripherals, examples, helpful, useful utilities. And also what I've done is I've written a score.py. So basically a very simple script that basically exemplifies scoring pipeline, or how you might score the Mojo. This is a very simple example, but imagine if I had wrapped this behind, say, a Flask application, or maybe, so for a RESTful service, that'd be a Flask application in Python, or maybe I use that actual score project, the local REST score. Okay, so again, we'll take a look, and what I'm going to do is, so as you can see in the bottom left corner, the environment that I have for my Python environment is activated, and if I do pip list, this is going to tell me everything that's installed in my pip environment, or Python environment. Now, as you can see, there's literally, or not literally, but almost nothing in the environment, and this is what I'm talking about in terms of level of dependencies and level of complexities that are required for deploying a model in production that Driverless AI tries to avoid. The only two dependencies, in fact, that we install is these two right here, DAI Mojo and data table. Both of them are open source, or well, DAI Mojo comes with Driverless AI and data table is open source. The rest are just kind of standard shipped with your virtual env. So they come kind of prepackaged. Now, what we're going to do is vim the score.py real quick and take a look at what's inside it. There's this one and this one, the two lines here that are basically imports, that are the important ones. The other one is just standard Python package, and this one is just a time package, because I wanted to show just like latency for scoring. And in reality, what it takes to score is 4 lines. We're going to look at this. In fact, I could do this in 3 if I wanted to. This one, this line here to load the model. So basically, all I'm saying is DI Mojo load this model from this path right here, and then load the data that I want from a file. In this case, it's loading from a file, but you could do download from use PyMongo to download from MongoDB into a data frame, and then finally predict. So 1, 2, 3, 3.5 lines basically gets you your predict method, or your prediction algorithm. not algorithm, excuse me, like prediction score. And if I run it, we'll do this, Python score.py. So just as an FYI, we did a little bit of metadata printing at the beginning. Basically, this is the UID of the model, when it was created, any kind of information about missing numbers, input columns, input types, output columns, output types. So this is just metadata. You didn't need it to actually score. And finally, we have the prediction steps. So the first thing we predicted, and it took maybe a thousandth and a half of a second to read the file, which is fairly small. It's only 15 lines. And it also took about 2.5 thousandths of a second to run 15 scores. So if you think of that from a high level, it's roughly millisecond level scoring. Now, I'm going to show you the complexity of this model in just a second, and you'll then understand a little bit more about what's like truly going on. But, you know, what I'm trying to drive home is just the level of complexity that we are getting in low level of time and with minimal dependencies from a software engineering perspective. So your machine learning engineer is really more focused on developing the infrastructure rather than having to rewrite Python code into Java or something, right? Cool. This is still going. Let's do this. Nope, I don't have password to this one. Okay. Well, we're just going to have to wait for this. Then let me see where I am here. Okay, so I was here. Okay, so unfortunately, there's kind of a small issue with the test server that I was using, which is that it restarted, and during the process of restarting, it does a test of all the like stuff inside that we've kind of run to just make sure that everything's working. Unfortunately, it is taking some time, and I don't want to waste anything here. So let's see if I can find let me try one more place here before I move forward. Let's see. So in fact, actually, while we're waiting, let's do this. Let's see if we can answer some questions while we're waiting for this to go.
Yeah, so we do have one that came in. It's a question related to the implementation of H2O within R and Power BI. Says, I've saved a Mojo model so that I could do a prediction without running H2O. Unfortunately, the model's saved under the path which contains a comma sign. Example, C /test folder, comma, /model _ mojo.zip. The compiler can't load the class folder. I was trying to go with escape sign, but it does not work. Is there any way to load the Mojo model using file name / path with commas and other characters?
Okay, so we're scoring in R. Okay, and I mean, so the first question I would ask is why is it that you don't just move the Mojo into a place wherein it doesn't have the comma? That would be my first inclination. Just move it somewhere better. But the other thing is that this is in likely, it looks like I would say likely Windows, which might also present its own special problems. If I remember correctly, there might actually be that Windows is not supported just yet, just because of the way that the kernels operate underneath the hood. But yeah, my first suggestion would in fact just be simply moving it. the mojo.zip should download to your downloads folder or whatever, and it's just, you know, mojo.zip. There should never be commas by our download process. So that seems like it would be downloading based on your locations settings. So in fact, I would just move it. That'd be my best explanation. And then you need to unzip it too. That's the other thing. So, you know, like unzip mojo, and then inside you actually want the pipeline.mojo file, not anything else. Yeah.
Great. So if anybody does have additional questions, feel free to type them into the questions tab. While this is loading, we can definitely answer as many as we can.
Okay, so in fact, there are a couple of things that I know that I've been asked in the past as far as, you know, can I score in this environment or can I score in that environment? You know, there are other things like, yes, the answer is more or less, apologize. I'm going to rally back to this, but yeah, avoid commas. It's essentially a path, right? So basically what's happening is that you're trying to load a mojo, and if I were to go here, it'd be something like, you know, mojo or model, and then load of some path here, right? Whatever dot mojo, right? One thing that you could do is in Python, you could probably try and do something along the lines of os.path.abspath. This will actually, you know, define the actual thing. It tries to grab it, so it determines what the correct encoding of the path is. So you can try that rather than just typing in manually. That could also be useful.
Are there any suggestions or best practices to estimate the required or minimum hardware for like RAM and CPU in particular to avoid the above mentioned errors, but keep the inference instance as small as possible? Good question.
Yeah, actually, this is a very good question. Specifically to the mojo, if your mojo is 1 gigabyte on disk, it will end up uncompressing to roughly 14 gigabytes in memory. Basically, the longest and most arduous process of loading the mojo is, in fact, that, loading the mojo. Once the mojo is loaded, the amount of memory required is actually quite minimal. So it's kind of like, if you think about it, almost like a skewed left curve, or right skewed curve, wherein there's like high requirements on heap memory down to a lower kind of base threshold. But usually a good math that I do in my head is 14 times the space of the mojo, pipeline.mojo on disk. So if I go here and I go to the cd mojo pipeline and I look inside ls-altr, what you see is that this file, pipeline.mojo, that's kilobytes. It's probably a couple megabytes, yeah, that looks right, just about 2, maybe 3-ish megabytes. So multiply that by 14, you get 42 odd megabytes RAM, which, you know, is fairly small. The one thing I wanted to exemplify, which I'm kind of struggling at the moment, is the complexity of what's actually going into this pipeline, which is quite cool. Let me see if I can get access to it now. Oops. No, well, it's progressed a little bit. But basically, that specific mojo actually has a lot of stuff going on underneath the hood. And it's one of the things I wanted to talk about, but basically the complexity of the model itself. If anyone has been familiar with driverless AI in the past, the one thing that is useful to make note of is that it does a ton of feature engineering. And by doing that, the level of complexity that goes into the actual mojo and how it operates is actually quite complex, regardless of how big or small the mojo is finally. And so what we're really trying to do, and the thing that I kind of want to stress about the driverless AI mojo as opposed to anything else, is the ability to do a lot of work without overwhelming yourself in terms of things such as dependencies, such as production environment complexity. Realistically, these are always things that you want to avoid. Increasing complexity is always a thing that you want to get rid of, you want to reduce. And this can mean anything. The amount of work that you have to do to build a feature engineering pipeline, for one. Basically, driverless AI models more or less eliminate the need for this, right? Because the model itself, the model artifact, comes prepackaged with the feature engineering pipeline. All that extra compute power that you would have had to previously allocate to a separate process of doing the feature engineering now gets packaged into a single process. So you're having a single JVM, a single Python process, single R script that does everything, rather than having you're pulling from the pipe of HDFS, compiling everything, then having, I don't know, Java process or Python process to do the feature munging, and then dump it into memory so that you can move the data from the Java feature engineering process into the Python or Java scoring process. Instead, everything is done in one kind of step, right? Which makes things quite effective, quite powerful from that level. Cool.
Please feel free to continue to ask questions as well.
This one's still not working. Oh my God. Okay. If anyone has additional questions, feel free to ask. In the meantime, I do apologize that this is one of those things that I guess we could call it, put it under the title of demo bugs, as it were, and kind of go from there. In fact, I may have. Okay. So I forgot about this. We have an appendix. Thank God for next appendix. So what we have here is basically a concept of like what is running during an experiment. So I do apologize that I can't give you a live image, but we'll kind of talk about this from high-level perspective, and hopefully we can get a little bit more clarity on insofar as what is going on, right? So if you think about that specific Mojo pipeline that I was talking about originally, right? This is how it gets created. Is driverless AI, you had some data that is loaded into your data set. It's then used in the experiment based on some certain level of tuning suggestions that you provide, either as expert settings, which is, think about it from a high level as having like complete control of your airline cockpit. You have all access to all the little knobs, all the little like levers and everything like that, as opposed to having the 3 knobs here, which is kind of like setting your Tesla for autopilot. You say, okay, I want the destination to look something like this, and then the car just kind of tries to get you there. So based on these knobs, and let me just kind of explain a little bit, these are fairly low settings. Accuracy of 4 is basically how much do I prioritize accuracy on a scale of 1 to 4, or 1 to 10, time the same interpretability as well. I really don't like this. Okay, cool. And we're back. Sorry, now that we're back, so the accuracy, time, and interpretability settings here are generally set to define the parameters of the experiment. What I really want to just drive home here is that this is fairly not non-complex, or like these are low settings. And even then, what we're seeing as far as like variable importance here is things like cluster target encoding or cluster distribution or truncated SVD, and you can see them by these little like tags on the front. The original columns are things like pay zero, limit balance. And the difference being is that they don't have this little tag in the front, meaning like what kind of transformation was actually performed on the values that be. So you can notice things like truncated SVD, things like cluster distributions, numeric to categorical weight of evidence. So these are all processes, all feature engineering techniques that we've applied to the model. And what this ends up doing is it basically increases the complexity. So if you think about, again, we're going to go back to my favorite slide here. Where is it? One more up. Here we go. If we go back to my favorite slide, that is this part right here. This concept of the featureization pipeline, or actually creating the features, and then the final model takes all of these, right? So inside the mojo itself is the ability to do this whole kind of process, and that's kind of what I'm trying to explain here with that slide, is the fact that there is kind of all these new features that we've kind of generated, and so that adds to the complexity of the model. And yet, even in that complex model, it would still be able to fit inside a couple megabytes package, like the 20-odd megabytes package that I showed you. That model was based off these settings as well, and so this level of complexity is, in fact, inside that model that I was working with earlier in terms of actual changes. Now we have questions.
Yeah, we got a question here. Are there noticeable performance bottlenecks when loading large data sets with the provided/mentioned Python libraries, especially when dealing with stream/time series data or images? Are there any forms of prepared pre-fetching tools?
That's a good question. Typically, the performance bottleneck in those cases would be with actually loading the data set. So the question then becomes, how do I want to score, right? Do I want to score row by row? Do I want to score in massive batches, right? So if you think about it from the row by row perspective, loading a single image or loading a single piece of data from time series is quite simple, right? It's just a row. Effectively, it's just a row, and you're kind of streaming that data in. So in real time, you may get chunks of like 3 rows at a time, or 2 rows at a time, 5 rows at a time. And in fact, that would, and excuse me, for time series specifically, this is not so much a problem, because the data is a row. And so essentially, the way I might consider it is, yeah, launch a REST server with an endpoint, and as the data comes in to maybe your SQL database, have a Python script that pulls just new data from SQL, and then run it against your the Python mojo. That could be an option. And in fact, that would be fairly low latency. It would also be fairly low cost, and the bottleneck would not be there. If you're loading massive data sets, so think about it now again from the higher perspective of million rows. So I want to score 1 million rows at a time, maybe 2 million, 3 million rows at a time. There would be, depending on how you decide to score it, definitely a bottleneck. If we think of it from a CSV perspective, how long does it take to load 1 million, 2 million rows into pandas? How long does it take to load, then score that in pandas? You know, and that's a design decision to begin with, like from an architecture perspective, but it also means that you require significantly higher resources, right? So, you know, if I needed to load a CSV, that means I have to put all the data into memory first, and then score it, which means that in most cases, my amount of memory that I would require for scoring this is the size of the data plus roughly the size of the data for scoring, right? And then plus the size of the loaded mojo. So the bottleneck truly isn't usually with the mojo itself so much as actually getting the data in. So now when we talk about like prepared prefetching tools, usually this is a question for your infrastructure because how would I phrase this? Like every company does data saving a little differently. Some people stick it in a SQL database. Some people stick it in no SQL database like MongoDB. Some people have it on HDFS. And each one kind of has their own distinct methodology for accessing the data, right? With SQL, you could do it with JDBC. With like HDFS, Hive, you can do it with Spark pretty easily. You basically can make a query to the Spark data, or to the cluster and get your data into a Spark data frame, which can then be scored. So it really depends on where and what your infrastructure looks like. Generally speaking, in most cases, there just needs to be, like, I would recommend using the APIs built by your data saving mechanism. For example, AWS, you could use S3, GCP, you would use, the Google APIs, or excuse me, for AWS, you use like Python Boto or, like the AWS Java implementation SDK. In things like SQL, you would use JDBC, which is pretty industry standard. In cases like Hadoop, you'd probably use Spark. Yeah. So that would generally be my recommendation. Again, think about it from the perspective of what I said initially, which is to have, here, let me see if I can find the slide again. Be sure to consider. So remember access to data, right? So the closer the score is to the data, the faster, more effective it will be. The score itself is just some process, right? Even if I think about this from like a scikit-learn perspective, right? Like I've loaded a pickle. This kind of holds true. This still is the same, is that if I can load the data on, load the model onto an HDFS edge node, it's easier to score my HDFS data. But if I want to maybe score data that is in Postgres and I load it into my HDFS cluster, it doesn't make as much sense, right? And so that's kind of the idea that I would get at, is that the bottleneck typically is going to be proximity to the data and infrastructure level rather than, with actual scoring. Yeah, cool. So let's try one more time. I want to see if I can gain access to this here. And if not, then we'll try and take some final questions, and then maybe we'll be done with it. Okay.
While we're waiting, if you do have any final questions, please feel free to start typing those in. Okay, certainly want to thank Nicholas for taking the time today and doing a great presentation. I want to thank everyone who joined us today and everyone who was asking great questions. The presentation slides and the recording will be made available on BrightTalk after this webinar is over. And we'll leave a few more minutes for some questions, but just want to wish everybody a great day and come back soon. Okay, we do have one last question here. How is the licensing process for the inference pipeline?
Oh, so this is a good question. The licensing is basically the same as with the driverless AI, like core platform. The best thing to do is probably ask directly to, the sales team. If you are, like directly involved with your sales team, reach out to your, rep. I would say they'll have like the best level, kind of high level discussion for you. But from the perspective of the license, the driverless AI license that you're provided from a trial perspective is useful for both. So if you're still trialing or still trying to make a POC and trialing the driverless AI product, then the trial license will work for both the Mojo or for the license for the pipeline as well as the product itself. In production, typically what we do is we allocate a specific scoring license, which is another discussion to have with your with your sales representative at that point in time. So I would probably say talk to your sales rep if you want specifically like in production scoring. If you're still trying to figure out how this works in production and like POC it, then you just feel free to use the trial license, and it will work up until expiry, of course, which I believe is 21 days from activation.
Okay, great. Thank you, Nicholas, and thank you everyone for joining. We hope you have a great rest of your day. That's the end of the presentation.